Hello everyone and welcome to another lesson. In this lesson, we will learn about forces. My name is Marilu Raduban and I'm one of the lecturers in the course 124103 Biophysical Principles. At the end of this lesson on forces, you will be able to define what a force is and identify different forces. Then you will know how to add forces graphically in order to find a resultant or net force. Also related to the topic of forces is how to find two sides of a right angle triangle given the angle, or how to find the side and an angle given one other side, and also most importantly how to break down forces into horizontal and vertical components. These three topics are dealt with in a separate video which you can check on stream. I'll talk more about that video at the end of this lesson. But so far, we have been talking about motion. We learned how to describe an object's motion in terms of its displacement, velocity, and acceleration. And this branch of mechanics is what we call kinematics. However, we did not really deal about what causes the object to move in the first place. So here we will now learn about dynamics, which deals with the causes of an object's motion. To answer this question briefly, what causes an object to accelerate? It is the quantity called force. Force is defined as a push or pull on an object. So in this figure here, this person is exerting a force on this object because he is pulling on that object, while this person is also exerting a force on this object because he's pushing on the object. If you think about it, the direction for which we push or pull on an object will determine where the object will move. Therefore, because direction is important, force is a vector quantity. Remember that for a vector quantity, you need to specify both the magnitude or the size and the direction for which you are exerting the force. The unit for force is called the Newton, and this is a derived unit which is a combination of the base units kilograms, meters, and seconds. 1 Newton is equal to 1 kilogram per meter second squared. 1 kilogram times meter per second squared. There are different kinds of forces that we can exert on an object to cause it to move. The first type of force is called contact force. Contact force essentially because there needs to be a physical contact between two objects. One who is exerting the force and the other object who is the recipient of the force. Examples of contact forces are friction, tension, and applied forces. So in this figure here, for example, this person is pushing on the lawnmower, exerting a contact force on it. The other type of force is called long-range forces because the two objects can exert force on each other without coming in direct physical contact with each other. Common examples of long-range forces are gravitational forces and electromagnetic forces. The different kinds of forces that we will encounter is summarized in this table, and we will go through each one in this lesson. So you have there the weight force with the corresponding symbol, direction, and equation. So some of the forces have equations associated with them, like weight force, friction, and elastic force. So this table is useful if you wanted to refer to this as you study forces. Yeah, this table can be a useful reference. All right, so let's go through each of these forces, starting with the weight force. The weight force, which we can write as W, or F sub g, is the force exerted by gravity that acts on an object that has mass. So any object that has mass, that's on the surface of the earth, experiences a weight force that's equal to mass times gravitational acceleration. So if the object is on the surface of the earth, the gravitational acceleration is 9.8 meters per second squared, which is the same g, or acceleration value, that we encountered when we learned about free fall. Right, so weight force, because it depends on gravitational acceleration, depends on position. So for example, gravitational acceleration on the moon is different from the gravitational acceleration on the earth. And so the weight force will be different in those different locations. Weight is a kind of force, so therefore it should be a vector quantity and it should have direction. The direction of the weight force is always directed downwards, because the gravitational pull is always towards the center of the earth, and if we are at the surface of the earth, we'll see that as a downward pull. Weight is also a force, so its unit is the Newton, which we've seen earlier. One important thing to note here is weight is not the same as mass. It's a little bit confusing sometimes, because in daily life we refer to weight in kgs. For example, if you ask someone, what's your weight, or how much do these apples weigh, we usually respond by giving something with a unit of kgs. So for example, what's the weight of this apple? And we say 1 kilogram. But in fact, we should be asking, what's the weight of this apple? Should be like 10 newtons for a 1 kilogram mass. So weight is different from mass. Weight is a force which has a direction and always directed downwards, and weight depends on the mass multiplied with the gravitational acceleration g. Mass is independent of position. It's a scalar quantity because you don't need the direction, and it is measured in kilograms. So the more correct question, if you wanted to know someone's how heavy someone is and you're expecting an answer in kilograms, is to ask, what is your mass? And they can respond with saying, my mass is 50 kilograms, for example. So mass is a measure of an object's inertia. Inertia, which we will encounter in the next lectures when we talk about Newton's laws of motions. Inertia is essentially the resistance of an object to changes in its motion. So the higher the inertia of an object, the more resistant it is to changes in motion. It's the same as saying as that the higher the mass, or the more massive the object is, the more difficult it is to change the direction of its motion. Or the higher the mass, or the more massive it is, the more difficult it is to move that object. So say you're moving here an elephant compared to moving several cats on a cart. Okay? Since the elephant is more massive, it has a higher mass compared to the cats, it will be more difficult to move the elephant, and you need to exert a greater force in order to move. Yeah. Right. So mass is different from weight. Weight is the force, mass is the object's inertia. All right, so let's try and solve this problem, or answer this question, to distinguish between weights at different places. So an astronaut's mass is 70 kilograms. What is the astronaut's weight or weight force on the Earth and on the Moon. So we're given here the gravitational acceleration on Earth and the gravitational acceleration on the Moon. You can try solving this on your own, and then you can come back to this video and listen to the solution. Alright, so weight, we said, is a kind of force, and it's defined as mass multiplied with the gravitational acceleration. On Earth, the weight of the astronaut should take into account the gravitational acceleration on Earth. So that will be 70 kilogram mass multiplied with the gravitational acceleration on Earth, 9.8 meters per second squared, and that gives you a weight of 690 newtons. On the surface of the Moon, where g is 1.6 meters per second squared, you do the same calculation except that g is now 1.6 meters per second squared. The mass is still the same. And so the weight will be different and it's 110 newtons. So notice that even at different locations, the mass is the same. It's always 70 kilograms, but the weight is different and it depends on the location of the object. Right? Okay, the second type of force, kind of force, is the normal or support force, which we indicate by capital N or F subscript N. So normal comes from the word norma, which means perpendicular. And it's the force that a surface exerts on an object with which it is in contact with. And that's why normal force is sometimes called the support force, because it's the kind of force that's provided by a surface that is supporting an object. So note here the keyword, there should be a surface, and that surface should be in contact with the object in order for you to have a support force. And because of the word here norma, which means perpendicular, the normal force is always directed perpendicular to the surface that is supporting the object. So say here you have this tire that's on the ground. So the ground is supporting the tire, so you will have a normal force. And the normal force is perpendicular on the surface and it's supporting the tire upwards. So your normal force is this upward force that is perpendicular to the surface that's supporting the tire. Also here we can see that the tire has a weight force, because any object that has mass will encounter a weight force, and weight force is always directed downwards. So regardless of the orientation of the object, the normal force is always perpendicular to the surface. So consider here a slope, and there's an object on the slope. The slope is supporting this object, so there is a support force between the surface and the object. And notice how the support force is perpendicular to the supporting surface. Right, so that's a perpendicular angle between the surface and the normal force. So normal force is always perpendicular to the surface. The next kind of force is called frictional force. It's the force that resists the motion of objects that are in contact with each other. And it's always parallel to the surface. So, and opposite the direction of motion. So frictional force opposes motion. So for example, here you have a lawnmower. It's being pushed to the right. So that's the direction of motion is to the left, sorry. So the lawnmower is being pushed to the left. The direction of motion is to the left. So the direction of frictional force between the ground and the wheels of the mower should be opposite the direction of motion. So the frictional force should be to the right, and it should be parallel to the surface, to the ground. There are two kinds of frictional forces: static friction and kinetic friction. Static friction is the friction experienced by any object that's at rest or that is static, and that's why it's called static friction. And kinetic friction is the friction that's experienced by the object when it starts to move. The next kind of force is called tension, and it's designated by the symbol capital T or F subscript T. Tension force is the kind of force that's experienced by any object that's being pulled by a string, a rope, cable, chain, or other non-elastic object. And the tension force is always directed away from the object. So say, for example, here you have a clown and he's pulling on the rope. If you want to find the tension force exerted on the clown, so that the clown is your object, then the direction of tension force on the clown should be away from the clown. So tension force is always directed away from the object. So for example, you have here a ball that's hanging on a string. Okay. And you wanted to diagram the tension force exerted by the string on the ball, then the tension force should be directed away from the object. In this case, because you're wanting to find the force on the ball, the object is the ball, and so the tension force should be directed away from the object or from the ball. Of course, it should be along the string, and that will be your tension force. Okay. There's also one other force acting on the ball or the object. Okay. Can you tell what other force is acting on the ball that's hanging by a string? If you answered that there is weight force acting on the object, then you are correct, because any object that has mass will experience a weight force, and weight force is always directed downwards. Okay. Because gravitational pull is always directed downwards. So in this scenario, an object hanging on a string, if you wanted to find the forces on this object, you have a tension force that's always directed away from the object, and because the object has mass, it will have a weight force that's always directed vertically downwards. The next kind of force is called elastic or restoring force, and it's the force on a spring or other elastic object, so like an elastic band or a rubber band. So anything that can easily stretch will experience elastic or restoring force. And the direction of the elastic or restoring force is such that to restore the spring to its original unstretched position. Restore the spring to its original unstretched position. Okay. So if you have here a spring that's originally unstretched, and you hang a mass, an object at the end, Naturally, because this object has some mass, it will have weight force exerted by the gravitational pull, and the weight force is directed downwards. Okay, this weight force W. And that weight force, the tendency of that weight force is to stretch. This originally unstretched spring. It will stretch it by a quantity delta x. Okay. Now the elastic force will try to restore the spring to its original unstretched length, and therefore the elastic force will be directed upwards this way, because it will try to restore this stretched spring to the original unstretched spring condition. And the relationship between the elastic force, the amount of stretch, and the amount of stretch is given by this equation, which is called Hooke's law. So Hooke's law gives a relationship between the elastic force and the amount of stretch via this equation. K is called a spring constant, which is a property of the spring, of how easily the spring can stretch, and delta x is the amount of extension from its unstretched length. Right, so in this case here, this is your unstretched length. Once your spring stretches to that length, you have this amount of stretch, which is called delta x. Now the negative sign in this equation is very important because it tells you about the direction of the elastic force. Meaning the elastic force is directed such that it tries to bring back the spring to its original unstretched length. Okay. So those are the different kinds of forces that we will encounter in our study of dynamics. And we said that force is a vector quantity, and when we consider the forces acting on an object, it's useful to be able to draw the forces. And as a vector quantity, we use arrows to represent the vector. The size or the length of the arrow tells us the magnitude or size of the vector, the force, and the direction for which the arrow is pointing at tells us the direction of the force acting on the object. By drawing all the forces acting on the object, we are able then to draw what we call a free body diagram. Okay, so a free body diagram is essentially a set of vectors, force vectors, that represent all the forces that are acting on the object. As I've mentioned earlier, the length of the arrow that represents the force vector reflects the magnitude or size of the force, and the direction of the arrow, where the arrow points at, is the direction of the force. It's very important that when you draw a free body diagram, you need to label each arrow to indicate the exact type of force. Is it a weight force, a frictional force, a tension force, an elastic force, and so on, a normal force? Right, so let's look at this example to sort of see how a free body diagram is drawn. I have here a stone or a rock that's sitting on this inclined surface, and it's also against this square block. And we want to diagram all the forces acting on the box. On the box. Okay, we want, let's change that to the rock. So we want to diagram all the forces acting on the rock that is at rest on a frictionless surface. Okay, so frictionless surface means that there is no frictional force. Right? So we do not have to include frictional force in our diagram. Okay, can you think of one force that's acting on the rock? Right, so the easiest one, any object that has mass will always experience a weight force, and the weight force is always directed downwards. So you have a weight force that's always directed downwards. What other force is the rock experiencing? Okay, the rock is being supported by this sloped surface. Okay, so there's a support, therefore there should be a support force or a normal force, and the normal force is always directed perpendicular to the surface. So you go from the surface and draw a line that's perpendicular to it. Okay, let's make that more perpendicular. Yeah, that's your normal force or perpendicular force. So that should be perpendicular to the surface, angle of 90 degrees relative to the surface. Okay, so you have the normal force, the weight force. Is there any other force that's acting on the rock? Okay, so note that there's a block here that's preventing the rock from sliding down the slope. And so in short, this block is also providing a support force on the rock. Okay. So there's a support force provided by this block. The support force should always be perpendicular to the surface. The surface of support is the block. So we should draw here, okay, perpendicular. Okay, so your normal force would just start from the center of your object. Right. So this is the normal force exerted by the block. All right. Okay, so you have the weight force always directed downwards and two normal forces acting on the block. So this one here is what we call a free body diagram. It shows you all the forces that are acting on the object. Okay, the forces are represented by arrows, okay, that show you the direction of the force. And the length of the arrow should correspond to the magnitude or how large that force is. Notice that you should also label your arrows or your vectors, because otherwise it's difficult to see what kind of force that is if you don't label your arrows. So it's very important to label your arrows. Okay. So we've been talking about forces as vector quantities. Vectors, they have magnitude, so you put the magnitude, which is essentially a number. Okay, how large the force is, followed by the unit, and you also need to have a direction. So examples of vectors that we have learned so far are displacement, velocity, acceleration, and force. And later on, you will learn about torque. Scalar quantities, on the other hand, only require the magnitude and of course a unit, and you don't need to specify the direction. So some examples of scalar quantities that we've learned is mass, distance or length, time, speed. Later on, you will learn about temperature and energy. They are also scalar quantities. Okay, some notes on vectors. As you already know, vectors are represented by the arrow. How long the arrow is tells you the size of the vector quantity. So tells you, for example, how strong the force is. The direction of the arrow tells you the direction of the vector. So for example, the direction of the force for which the force is being exerted. A negative of the vector will have the same length but opposite direction. Okay, so for example, this is vector A and that's vector B. Vector B is the negative of vector A. So when you say negative, it's only the direction that flips, okay, but the magnitude stays the same. A vector is only the same if it has the same length and the same direction. So these two vectors here are the same. While these two vectors are not the same because although they have the same magnitude, they have different directions. But sometimes or often, like we've seen in the example of the rock on the slope, there is more than one force that's acting on the object, and we need to know the overall effect of that force. In that case, for us to know the overall effect, we need to add the forces up. Okay. And because forces are vectors, in other words, we need to add the vectors together. And the direction of the overall effect of the vectors after adding them will determine the direction of motion. So now we will learn about vector addition and subtraction. And there are two ways of doing vector addition and subtraction. In this video, we will learn about the graphical method. And in a separate video, you will learn about the component method. But first, the graphical method. It's called graphical method because essentially you will be drawing the vectors. So say you have here two vectors, vector A that's pointing upwards and vector B that's pointing to the right, and you want to add those two vectors to determine the overall or the net, what we call net or resultant vector. Okay. So net or resultant vector is the vector sum to find the overall or the net effect of those two vectors when they're added together. So we want to find A plus B. In graphical method, you essentially join up the vectors sequentially, but you join them up from head to tail. Okay, so say you draw vector A, so vector A goes upwards. Okay. And then for vector B, you put the tail of vector B on the head of vector A. Right. So you draw the vectors sequentially. Okay. The tail of the second vector starts from the head of the first vector and you go vector B's to the right. It's the same direction. Okay. The resultant or the net vector is drawn from the tail of the first vector to the head of the last vector. Okay. So if you draw that, you have here the resultant vector. So this resultant vector gives you the overall effect of those two vectors when they're added up together. So in graphical method, you need to draw your vectors to scale so that vector A should have the correct length and vector B should also have the correct length, so that when you join vectors A and B going from the tail of vector A to the head of vector B, all you have to do is to measure the length of this resultant vector. Okay, you measure the length and the length will tell you the magnitude of the net vector. And then for the direction, what you need to do is to measure the angle relative to the horizontal axis. Okay, so when we say relative to the horizontal axis, we actually mean relative to the positive x-axis. Right. Okay. So remember your coordinate system. This is positive x. negative x, positive y, negative y. And so if you have a vector, like that, then you measure the angle from the positive x-axis. So that will be the angle theta. Just angle theta. Right? Note that when you're drawing the vectors graphically and you're adding them, you should not flip the vectors when you're adding graphically. So notice how the orientations of vectors A and B are the same, except that you just draw them sequentially one after the other. Because the moment you flip the vectors, what you're doing now will be what you'll do now will be vector subtraction once you flip one of the vectors. So let's look at vector A minus vector B. Okay. So it's the same procedure for graphical method. You draw the vectors one by one sequentially. So vector A, it's that same vector. Now you draw vector B, but this time you're subtracting. So there's a minus sign there. Okay, and as I've said earlier, a negative of a vector will be the same vector except that the direction is opposite. So then if you draw vector negative B, it will be the same vector B except that the direction is now flipped. The direction is opposite. But you're still going from the tail of vector B should start from the head of vector A, drawing the vector sequentially. And the resultant or the net vector still goes from the tail of the first vector to the head of the last vector. So this red arrow here will be the resultant vector or the answer to A minus B. Okay. If you've drawn vectors A and vectors B with the correct length, all you have to do again is to measure the length of the resultant or net vector, and that should give you the magnitude or the size of A minus B. And then to give the direction, you should measure the angle from the positive x-axis going that way. From the positive x-axis to the resultant vector, and that will be the angle theta, which tells you the direction of your resultant or net vector. Okay, so the important thing when you're subtracting, you need to flip the negative vector. Recall that if you go A minus B, that's equivalent to saying A plus negative B. So it's like you're adding negative B to A. So it's vector addition except that you have vector B in opposite direction. That's why we flipped vector B when we drew these vectors here. All right. Okay, let's look at this example to see how we add vectors graphically to find the resultant or net force. So there is a skier who is going down a smooth slope, and we want to find the overall effect of all the forces that's acting on the skier. In other words, we want to find the resultant or the net force by adding up all of the forces that's acting up on the skier. Okay. So the clue here is smooth. When we say smooth, then friction is negligible, and so you can say that there's no friction, or we will not include frictional force in our free body diagram. Okay, so let's start drawing the forces, all the forces that's acting on the skier. Can you think of one force that's acting on the skier? All right, any object that on Earth that has mass will have weight force, okay? And weight force is always directed downward. So you have that weight force there, that's downwards. Okay, the skier is in contact with this slope. So the slope is providing some kind of support to the skier. So you'll have a support force or a normal force. And the normal force is always perpendicular to the supporting surface. So that's perpendicular. That angle is 90 degrees. Is there any other force that's acting on the skier? Right. Okay, there's no frictional force because the surface is smooth. Okay. Right, so that's all of the forces that's acting on the skier. Okay. There is no one common misconception that I often encounter is to say that there is an applied force. But in this case, there's nothing is pulling or pushing on the object. So in this case, there's no applied force. The skier is just going down the slope through the influence of the gravitational pull. So there's nothing pulling or pushing on the physically pushing or pulling on the object in direct contact. So there is no applied force here. There are only two forces acting on the skier. That's the weight force and the normal force. And you can draw the free body diagram this way. You don't have to draw the skier and the slope. You can just represent the skier as a point. And the weight force is directly vertically downwards, and the normal force is perpendicular to the surface. Of course, there's a surface, an imaginary surface here where you measure the normal force to be 90 degrees relative to that. Okay, we want to find the net force or the total force or the resultant force of these two forces. So you draw the forces sequentially from using the head to tail method. Okay, so you have the normal force, same orientation. And then for the weight force, you draw the second vector such that the tail of the second vector starts from the head of the first vector. So that's the weight force. And the resultant force goes from the tail of the first vector to the head of the last vector. So that's the resultant or the net force. Okay, and the angle is measured relative to the positive x-axis. Okay, so the angle will be this theta angle here going from positive x-axis to the resultant force or the net force. Okay, so why did we want to find this resultant or net force? This net or resultant force indicates the direction of motion where the skier is going. And so notice how this resultant or net force is directed this way, and so the skier goes down the slope in this direction. So the skier goes down the slope in this direction. Okay. There's also a way of finding the resultant force from the free body diagram, and this is called the parallelogram rule. What you can do, that's why it's called parallelogram rule, because using these two forces, you sort of draw a parallelogram. Okay. If we copy the normal force like so, it should be the same length. So because we're just copying the normal force from here to here, so the length should be the same. And then we copy the weight force onto here. Okay, and so we're forming this parallelogram. The resultant force will bisect the parallelogram like so. Okay, and notice how the resultant force is the same as what we obtained by doing the head to tail method, and it's still the same direction and magnitude, and it still means that the skier will go down the slope in this direction. Okay, so this is another way, but this parallelogram rule sort of works only if you have like two forces that are involved and you're wanting to get the resultant force. If you have more than two forces, like if you have three forces or more, then you have to draw using the head to tail method to find the net force. Right? Okay, so that's the graphical method. The other method of finding the resultant or the net force is called the component method. And in this method, you need to add vector components. Okay? So if this is your vector can be divided into a horizontal component or x component AX and a vertical component or y component AY. And if you have, so this is for one vector, if you have two vectors, you need to consider the horizontal components of each vector and the vertical components of each vector. And you add up all the horizontal components and all the vertical components together. How to find the horizontal and vertical components? You'll need to use some trigonometry given the angle theta. Okay, and that's the subject of the video on stream on the trig refresher. I would direct you to the video on stream about trigonometry and about how to obtain the components of the vectors. Okay, and then in the next lecture, when we go now to forces and Newton's laws and we apply vector free body diagrams and solving vectors, then you will apply what you've learned on components of vectors. All right, so I'll end our lecture because we've gone up to how to find the resultant force using graphical method head to tail, but please do watch the next video on trigonometry and finding the components of a vector. That will be really crucial in the next topic on forces, where we now apply what we've learned on vectors and components to find net forces as applied to problems. Right, so that's it for this lecture. And yeah, I'll see you in the next lecture.